Hey, okay, so let's switch gears here and let's go from ethers to epoxides. So epoxides are kind of similar to ethers as far as the atoms that are involved in their structure, but the reactivity is quite different. So nucleophilic substitution reactions of epoxides. Okay, remember from Orgo 1 that we can make epoxides by reacting an alkene with a peroxy acid. Okay, to get an epoxide. So here's just the same structure written a different way, skeletal form on the bottom. Or we can also react an alkene with something like chlorine, Cl2, okay, to add to the double bond of chlorine at one carbon. Water will add to another carbon, and then you can do an intramolecular reaction to get the epoxide. Okay. Stop the video, write everything down, okay, as needed, okay. So, the reason why epoxides are more reactive than ethers is that the three-membered ring, three-membered epoxide ring, okay, is strained. It doesn't, if something can react with it to open up the ring and release the strain, it will. Okay? So, example, once a nucleophile, okay, attacks and opens the ring, the strain is released. Okay, so that's a major driving force for these reactions. Okay. Like everything else so far, you got SN2 and SN1 reactions. Okay, if we react in epoxides, so substitution reactions of epoxides under acidic conditions. The substitution reactions of epoxides under acidic conditions are what we call SN1-like. Okay. So the same thing that determines the reactivity for SN1 reactions are going to determine the reactivity for reactions of epoxides under acidic conditions. Okay. One example here would be this epoxide. And let's go ahead and add 2 carbons here. Okay. And if we reacted it, say, with hydrochloric acid in ethanol. Okay, hydrochloric acid in ethanol. Our major substitution product after nucleophilic attack will be this alcohol. Okay, so this is where our nucleophile came in. This is what's remaining of the epoxide, the alcohol. Okay, let's take a closer look now at why we have nucleophilic attack on this carbon, so this carbon, instead of this one. Okay, so if we look at the same epoxide, so let's write the mechanism right under that example I just gave you. The first step is going to be reacting with the acid. So the basic lone pairs on the oxygen attack the acid, okay, to protonate it, and then chloride leaves. And the only thing that's changed here is our epoxide is protonated now. Okay. Now, plus Cl minus. Keep in mind that ethanol was our solvent. Okay, so it's present in a very large concentration compared to everything else. So we keep that in mind here. Now it is a weak nucleophile, but remember, under protic conditions, so is chloride. And we say chloride is not strong enough to attack an ether. Under these conditions, the ethanol is going to be our primary nucleophile. Okay? So what we have to decide is if it attacks this carbon or this carbon. Remember we said that under SN1 conditions, under acidic conditions with epoxides, the reactions are SN1-like. So if I were to break one of these bonds and put a carbocation there, if I broke this bond and put a carbocation there, it would be secondary carbocation. If I broke this bond instead, I would have a primary carbocation, which is less stable. Not good. Because of that, even though I do not officially form a carbocation here, there is more positive character on this carbon. So we can say this bond is partially broken, there's more positive character here. That's where the nucleophile attacks, where there's more positive character. So it's SN1-like because there's more positive character at that carbon, because it would be a more stable carbocation if it completely formed. So nucleophilic attack forms a new oxygen-carbon bond, and then I open the epoxide ring. So here's my new oxygen-carbon bond. Everything else stays the same with the nucleophile. It's protonated now because oxygen has 3 bonds. Well, not protonated, I'm sorry. It's got a positive formal charge. And now I've got my alcohol on the other carbon. Okay. The very last thing to do here is just deprotonate. I can use chloride, or I can use another solvent molecule, does not matter. Deprotonate to get the final product. You don't have to write it exactly like me. You can write it however you want to, as long as it's the same compound. So keeping what we just talked about in mind, what would be the product here? Okay, if I took something like this. So here's my epoxide, just written differently. Okay, and I reacted it with HBr. Okay. Reacted it with HBr. So remember here that this is acidic conditions, and that tells us SN1-like. Okay, it tells us that my nucleophile, which in this case is bromide, it's strong enough, is going to attack the carbon of the epoxide that would produce the most stable carbocation, which would be this one, okay, instead of this one. Or you can say, under acidic conditions, the nucleophile attacks the most hindered carbon of the epoxide. Okay. So my major product, once we're done, would be that. Would be that. See what's next on epoxides. Okay, so this is acidic conditions. Let's talk about what happens under neutral or basic conditions. So substitution on epoxides, okay, under neutral or basic conditions is going to be the opposite. It's SN2. Okay, SN2. For example, if I take the same epoxide as earlier, here, and instead of reacting it under acidic conditions, say HCl with ethanol, I chose to react it with ethoxide. Ethoxide. That's a strong nucleophile, right? Under neutral or basic conditions. SN2 reaction tells me the nucleophile will attack the carbon that's the least hindered, the carbon that's the easiest to get to, and in this case it's this carbon. It's over here by itself as opposed to this more hindered carbon. So the final product will have nucleophilic addition or attack here, and then my alcohol, after I open the ring, will be on this carbon. Okay, so that would be the product. So now let's erase this and let's look at the mechanism of how it happens. There's no protonation here. Okay, it's just just going to be direct nucleophilic attack onto the epoxide. Okay, so SN2, my nucleophile, will attack the carbon to form a new oxygen-carbon bond at the least hindered site. That will cause the epoxide to open up. And the immediate product from this reaction be this. Okay, so I'm not quite there yet. I need to protonate that oxygen that's got the negative charge on it. And here, any species that has an acidic hydrogen in the reaction mixture will work. If there's any water in there, you can use water. If the solvent in this case was ethanol, you can use ethanol. Okay? Any proton that we can find will work. So I will use ethanol here. So this basic oxygen, the basic lone pairs, will grab a proton to give you the final product. Okay. And we're done. Any proton source will work. Don't get caught up on that. Just remember that under neutral or basic conditions, my nucleophile attacks the least hindered carbon because it's SN2 chemistry. Okay. So let's put it together. Let's put it together. I want you to give the major product. Okay. Give the major product here. And I'm going to give you one epoxide. Okay, there's one epoxide. And I'm going to react it under one set of conditions with HCl and methanol. And I'm going to react it under another set of conditions with methoxide in methanol. Okay. So pause the video now and fill in the final product here and the final product here. Okay. Acidic conditions, SN1 like. After protonation, chloride is not a strong nucleophile, so methanol will be my nucleophile because it's a solvent in this case. Okay, solvent and nucleophile. So I'm going to attack with the nucleophile at the most hindered carbon that would give the most stable carbocation if one were to form, which would be this carbon. So my final product, this methyl group's attached to this carbon, it's still there. The alcohol's here, okay? Now I have the same two methyl groups on this carbon, and the nucleophilic attack gave me this. Okay. So the nucleophilic attack occurred on this carbon under SN1-like acidic conditions. On the bottom, we're going to get the different product. That was my phone. We're going to get the different product. Now, it's SN2 chemistry. The nucleophile, the strong nucleophile, will attack the least hindered carbon that it can. There's only one methyl group here. There's two here. Okay. So nucleophilic attack will happen here. The alcohol that's left will be on this carbon. Whoop. Carbon, the two methyl groups, and then the alcohol. Knowing these two conditions is very important because if you're given one epoxide and asked to give a specific product, you've got to know the conditions that allow you to give either one. You've got to know the difference between the SN2 and the SN1-like conditions.